Hello, good morning, student. I hope you all are very happy, healthy, and fine at home. So, yesterday we have discussed about the protection and deprotection of amine groups. Most of the important four protecting group, as well as in addition to that we have discussed some another protecting group which is used for protection of the amino group. So today we are going to discuss about protection and deprotection of carboxylic group. And as we know that carboxylic group C double bond O is a functional group. Functional group means what? The site of reaction or the atom or group of atom that determine the physical as well as chemical property of the particular family of the organic compound is known as a functional group. So this acid group is also present in the what we can call it as a peptide synthesis. It is widely used as a protecting group. So this carboxylic group, how it is protected, what are the protecting group used to protect this carboxylic group? Number one, it is converted, this carboxylic group is converted into as a ester. When it is converted into as a ester, then its reactivity is decreased. Why the reactivity is decreased? If you look at here, this proton hydrogen or this proton is highly acidic in nature, and therefore it generates the problem of chemoselectivity. Chemoselectivity means in a basic condition we cannot carry out this reaction because these hydrogen atoms are highly acidic in nature. Similarly, nucleophilic attack on this such type of the reaction also get affected due to the interference of this acidic proton. And to avoid such problems, to get the desired product, we must protect this carboxylic group by using some of the suitable reagent, and the reagent should be introduced under mild condition, and it should be removed under mild condition, as well as it should be stable at oxidizing, reducing, or in acidic medium or basic medium. That are the some of the what we can call it as a criteria for the ideal protecting group. So by keeping this point into mind, we are going to discuss this as. Let us see to get the desired product. For example, let us see here carboxylic group. We know that the general formula of acid is just RC double bond OH, right? This is a general formula of carboxylic acid or the acid, where R may be alkyl group or the aromatic group. Suppose if you treat this with PG is nothing but as a protecting group, and this protecting group, there are the number of protecting group used to protect the carboxylic group, because this proton is highly acidic in nature and it interferes the most of the reaction, and that's why there is a need to protect the carboxylic group, and we can carry out the reaction at the other end and we will get the desired product. Suppose this will be treated with some reagent and you are going to get here R C double bond O, then O Me, that is called as a methyl ester. This one is known as a methyl ester, right? And protecting group should be here alcohol in presence of the acidic condition, so you will get as a this type of the product over there. And suppose it is treated with some other reagent, you are going to get here R C double bond O Et. This is known as a ethyl ester. This is known as a ethyl ester. So here esterification reaction, just alcohol, ethyl alcohol in present catalytic amount of acid, you will get as a ester. When it becomes as a ester, the reactivity of that carboxylic group becomes as a less. And let us see another one. Suppose it is treated with some reagent, so that you are going to get here R. We are talking about the general reaction, what will be the possibilities to convert this. So O, then here maybe this is called as a tertiary butyl ester. This is known as a tertiary butyl ester, right? Tertiary butyl ester. Or you can treat with some other protecting group, so that you are going to get here R C double bond O, then O. This is a allylic ester. You are getting allylic ester, that is formed here. Or if you treat with some protecting group, you will get R O, then PH, then it is called as a phenyl ester. This one is known as a phenyl ester. Or if it is treated with some reagent, you will get this type of the compound, that is pH, that is called as a benzyl ester, right? So these are the some of the derivatives I am written over here. If you observe this structure carefully, what do you see here? All these reaction taking place in presence of catalytic amount of acid. This we can introduce. If you use here methyl ester, we are getting, just you treat this compound methanol in excess amount in presence of the acid, you will get the methyl ester easily. That protecting group here, this PG means here protecting group. If you use here methanol MEOH in presence of the H plus, you will get heat it, you will get as this type of the compound methyl ester. And now this one, instead of methyl, if you use ethyl alcohol, catalytic amount of acid, you will get as ethyl ester. Similarly, if you use here this type of the compound, suppose as this one C double bond in presence of H plus, you will get as a tertiary butyl ester. And here this compound, suppose HO, then this one allylic alcohol in presence of H plus, you will get this type of the allylic ester. If you treat as a phenol in presence of catalytic amount of acid, you will get as a phenyl ester. Similarly, if you take as a here benzyl chloride you will, or benzyl alcohol in presence of H, you will get as a benzyl ester. So these are the some of the general reaction which is acting as a protecting group for carboxylic group. Right? Now let us move on to the first point we are going to learn here, protection of carboxylic group as an tertiary butyl ester. Right? This is the general introduction we have seen here. Now we are actually starting the tertiary butyl. First one, tertiary butyl ester. Tertiary butyl ester as a protecting group for, as a protecting group for, protecting group for for carboxylic acid, for carboxylic acid. Now this, and as we know that starting compound, or the, for example, suppose we have a RC double bond O, OH. Here this hydrogen atom is highly acidic in nature, therefore it make the problem for the chemoselectivity, interfering the reaction, and therefore this will be treated with this one, C double bond O, H plus. What you are going to get here? You are going to get here R, C double bond O, and this tertiary butyl group, that is a protected carboxylic group. This proton we replaced by that bulky group. This tertiary butyl group is a very bulky group, and therefore reactivity of that ester becomes as a very low. And now when it is treated with H plus, the reaction we will get RC double bond OH, that is a carboxylic group get free here. We will get our original compound, and the side whatever reagent tertiary butoxide we have used, we are getting as a this one. Do you know the name of this compound? The name of this compound is a isobutylene, or we can IUPAC name of this compound. Suppose 1, 2 and 3. So there are the 3 carbon atom in a straight chain, and therefore at 2 position there is a methyl group. So we can call it 2-methyl, 3 carbon atom in the straight chain. So prop. At 1 position there is a double bond, so we can call it as a ENE, propene. Prop 1E. Sorry, I think prop 2-methyl prop 1 ENE, or 2-methyl propene you can call it. So this is a IUPAC name. So we are now, this is a general reaction we have seen. Now let us look at as a mechanism of protection. Mechanism of protection. Look at how this get protected. Let us see. First one is this one, starting compound is this one. The name of this compound is a 2-methyl propene 1 ENE, or we can call it as a 2-methyl propene, and then that will be treated with H plus. So this H plus, this carbon-carbon double bond, as we know that it is a nucleophilic in nature and it is acting as a electrophile. This nucleophile abstract this or attacking on that H plus. What do you get? You are going to get here this positive charge over there, because CH3, and as we know that it becomes as a tertiary carbocation. This is a tertiary carbocation, and as we know that the stability order of carbocation, tertiary carbocation is more stable than secondary than the primary carbocation. Therefore, this tertiary carbocation is more stable because this is stabilized due to the plus I inductive effect here. And now we know that here R C double bond O H, this lone pair which is present on nitrogen atom, that non-bonding electron pair attacking on that. Always remember, lone pair is nothing but they are the nucleophile. Now it becomes as a electrophile in nature, and therefore we are going to get here the product, this one R C double bond O here H, then this tertiary group. Now look at on the oxygen atom there are the 3 bonds, and therefore positive charge comes on that oxygen atom. Whenever positive charge comes on any heteroatom, that species becomes as a very unstable. It trying to stabilize, so this it is losing the hydrogen atom here, neutralizing that positive charge. We are going to get here RC double bond O and this tertiary group, right? Now this tertiary group, this is a protected carboxylic acid, because that isobutyl in presence of H plus is used to protect the carboxylic group. Now let us look at as a mechanism of deprotection. Next one is the mechanism of deprotection. Here, mechanism of deprotection. Protection. Mechanism of deprotection. And for that purpose, you take down that example. Now R C double bond O, then O, this tertiary group over there. And as we know that deprotection can be done in presence of acid, so we can remove this tertiary butyl under the acidic condition. Now we are treating this compound in a catalytic amount of acid. The lone pair, there are the 2 oxygen atom, and therefore the lone pair which is present on that oxygen atom as well as on this oxygen atom, any one of them will use to attack on that H plus, and you are going to get here R, then C double bond OH, positive charge over there, then O, then this tertiary group. And now this positive or one of the hydrogen atom can be lost here, forming double bond over there, and this bond is breaking, forming double bond over here and neutralizing this, and you are going to get here the product RCOH double bond O, that is acid back, and then C double bond O, this isobutylene we are getting as it is here. In this way we can show the representation of the mechanism of protection as well as mechanism of the deprotection. Now let us take down the one example which can clearly shows the how this protection is useful for the protection of carboxylic group. Let us see here one of the example. H2N, then C double bond O, then this, then C double bond O, OH, right? Now if you look at this structure carefully, what do you see in this structure? This structure clearly shows that there are two functional groups are present, one which is acid and another one which is amide, right? And as we know that reactivity, according to your opinion, which group is more reactive in nature, amide or acid? So among these two, acid group is more reactive than the amide, that you remember. Now if this group if you want to reduce this group by using, that is boron trifluoride in presence of THF, tetrahydrofuran, you might be knowing as a tetrahydrofuran. Structure of the tetrahydrofuran is this one. This is the structure of tetrahydrofuran. Tetrahydrofuran, it is used as a solvent in many organic reactions. So this we know that it is a reducing reagent. Just like as a reducing reagent we are using as a sodium borohydride, lithium aluminum hydride. These are the reducing reagent which can reduce the carbonyl group into, but in case of the sodium borohydride and the lithium borohydride, sodium borohydride only reduces the carbonyl group. It does not reduce the what we can call it does not reduce the acidic group, acidic carbonyl group or the amide group. And that a strong reducing reagent like lithium aluminum hydride, it can reduce most of the functional group, like as in addition to the carbonyl group of that aldehyde and ketone, it can reduce carbon-carbon triple bond, amide group, carboxylic group, ester group into their respective groups. So here remember, this is a reducing reagent which can reduce carboxylic group into as a alcohol, so that you are going to get here H2N, then double bond O, then this one C double bond O, that get reduced CH2OH. What we did, this is a reagent used to convert carboxylic group into as a primary alcohol. Here you are going to get as a primary alcohol. But we want to keep this group intact, and we want to reduce this amide group into as a amine. How will you do this reaction? Suppose if you want to this type of the reaction H2N, then this one C double bond OH. So we want to prepare this compound. We don't want do not require this. We want to prepare this one. How do you prepare this? We reduce this selectively, and for that purpose, as we know that this one is a more reactive group. It is a more reactive functional group. It is a less reactive functional group, and whenever such type of the reducing reagent is used, they can reduce the more reactive group into the respective functional group, but less reactive remains as it is. Now we want to prepare this one. We want the carboxylic group as it is, and we are going to convert that amide group into as a amino group. how would you do? So you can think about the first protection and the deprotection. We can protect the carboxylic group first, and then we can prepare this one. And just now we have seen the protection by using as a this one, tertiary butyl ester, right? That tertiary butyl ester is used to deprotect the used to protect the carboxylic group. Let us look at here this one. Again you can draw here H2N, C double bond O, this CH2, then C double bond O, OH. This will be treated with this one, C double bond in presence of H plus. And as we know that this is the reagent used to protect the carboxylic group, and therefore H2N amide group remains as it is. So C double bond O, and then this one, right? And now this is a protection, and now you can treat this compound with BH3 in presence of THF, tetrahydrofuran. What it will do? It will reduce this group now into H2N, and this C double bond O, then this is a tertiary group, right? And after that one extra step is added over there. Then now you can treat with just as a H plus, that is the deprotection can be carried out under the acidic condition, and what you are going to get, your target molecule means your desired product H2N, then this C double bond OH, that is your original product. So this is a speciality of this tertiary butyl ester. So in this way we can carry out the reaction and we will get the desired product. Now let us move on to the next point, that is a second one. What is that second one? Second one will be the silyl ester. Second one will be the silyl ester as a protecting group, for carboxylic acid, right? And as we know that TMS means what? Tetramethyl right? TMSCl you can write, tetramethyl chloride. And this, you already familiar with this structure, as we already use while using as a carboxylic group, right? So there we already seen that the protection for the carboxylic group, right? That silyl chloride, and that silyl chloride is introduced under acidic condition, as well as it is removed under acidic condition also. So in this case both way we can prepare. Now let us look at here, as we know that general formula of acid is RC double bond OH, right? This is a general formula of acid, and that will be treated with TMSCl. What do you get? You are going to get here RC double bond O, then TMS. And as we know that trimethyl silyl chloride, the full form of this is a trimethyl silyl chloride, right? Silyl chloride. and that silyl chloride trimethyl means Me3SiCl. So this is a structure of trimethyl silyl chloride, or instead of this you can show like this RC double bond O, then O SiMe3. SiMe3 means silyl. This is a protected carboxylic group, and as we know that silicon deprotection can be carried out using ammonium tetrabutyl ammonium fluoride or potassium fluoride, because silicon has a great affinity toward the silicon. Fluorine and silicon, they have a great affinity, and that's why there is a driving force to deprotect this one. Or in an acidic condition also it get cleaved very easily, and we will get the acid back. Suppose if you treat this compound in presence of acid, you will be getting here RC double bond OH, and that is silyl chloride. Or we can use here BU4NF, that is the tetrabutyl ammonium fluoride, or you can use as a KF, potassium fluoride is used to protect this one. Now let us look at as a mechanism, how mechanism takes place here. So first one, mechanism of the protection. First one, mechanism of protection. Mechanism for protection means this one, how it takes place here. Let us see in presence of acid it is introduced. So we are going to get here R, then C double bond O, then H plus trimethyl silyl chloride Si. Here you can write Me and Me, right? Now lone pair which is present over there is going to attack on silicon. Departure of the chlorine atom from here, you are going to get here R, C double bond O, H positive charge on it, silicon, then Me and Me. When, as I already told you that when positive charge present on that heteroatom, that species become highly unstable. It tries to stabilize it, and that's why losing the proton over here, 1H from here and Cl from here, that goes in the atmosphere. You are going to get here R, C double bond O, Si, then this one Me and Me, right? So this is a structure protecting group of that carboxylic group. Now let us look at as a mechanism of deprotection. This is a mechanism of protection. Now is a mechanism of deprotection. Mechanism of deprotection. For that, take down this structure once again. R, C double bond O, Si, then Me and Me. Me is nothing but as a methyl, and that will be treated with acid. Therefore, the lone pair which is present on here, what do you get? Or lone pair present on that oxygen atom, it can be pick up that proton, and you will get R, C double bond O, H, or specifically you can show that proton here OH, pick up the proton from here, and you will get R, C double bond O plus, then O, Si, this one Me and Me. Now this bond breaking from here and this neutralizing, you are going to get here R, C, OH double bond O, that is acid back over there. In this way we have done here the mechanism of protection as well as mechanism of the deprotection. Now let us look at the specific example to illustrate this point more precisely or clearly. Let us see here, suppose we have this type of the compound. Consider here, for example, we have this structure, this one, then OH, or for sake of convenience draw the structure cleanly here, C double bond, then this one, C double bond OH, here maybe not this one, let us see here, this one, C double bond OH, and one more functional groups are. If you look at this structure, if you observe this structure carefully, what do you see? How many functional groups are here? Look at here, OH functional group, carboxylic group functional group, as well as carbon-carbon double bond. There are the three functional group present over here. If this compound get treated with, suppose that is acetyl chloride, C double bond O, Cl, what do you get? You actually going to get here C double bond O, then this one, C double bond O, then O, CO, CS3, and that OH remains over here. Suppose you want to prepare this type of the compound instead of this one. Let's see here, O, CO, CS3, then this one, C double bond O, OH. We want this group, acid group is back, we want to protect only as this group. How could you prepare this? If you use the acetyl chloride, you will get the straightforward this type of the product, but we require this one. This is our desired product. To synthesize this product, we don't require this product. So how will you prepare this compound? So let us see. So the answer for that, we can use the silyl ester as an protecting group, so that we will get the this our desired product. Now let us look at here. First one, what we are going to do here? First one, we are going to treat this compound in presence of silyl TMS, tetramethyl silyl chloride. So what will happen? It is going to attack on that Cl departure. It alcohol is there, but we can use here only as a one equivalent of trimethyl silyl chloride. If you use in excess amount, it will not get, because here also look at, there are the three functional group. Out of that three functional group, which one is a more reactive one? Acidic group functional group is a more reactive than OH group, than the carbon-carbon double bond, and therefore if you use as a tetramethyl silyl chloride in a controlled condition, one equivalent, so it will protect this one, so that we are going to get here this OH remains as it is, then this one C double bond O, then Si Me3, right? This is a protecting carboxylic group, and this further treated with this one acetyl chloride in presence of maybe it does not require as a Lewis acid. So what is going to happen? This is going to attack over there, this revolving there is a HCl fumes goes in the atmosphere, so that you are going to get here this product, then O, then COCS3, this acetyl group, and then C double bond O Si Me3, right? And after that, deprotection can be carried out or can be done by using as a acid or Bu4NF or KF, that is fluorine atom F minus is attacking on that silicon, and then which will take the proton from acid, and you will get the our final product, maybe this one COCS3, then CH2 double bond O and OH. So this is the final product we got here. So I think we have seen first protecting group for the carboxylic acid, remaining protecting group like as a DCC or DCCI or DIP, CP, DI, that we will see in a next lecture. Let us stop today here. Thank you. Have a nice day.